Hi, welcome to this new session on stochastic inventory management optimization. So far, we have seen a deterministic inventory model, which was the EOQ model. Then we saw a very simple probabilistic inventory model, which was our news vendor problem. We went into the time axis and extended the time axis to a finite time horizon and discussed a deterministic dynamic inventory optimization problem, which was solved using the dynamic programming formulation, the Bellman equation. And now this is going to be the last session on the inventory management, which is on stochastic dynamic inventory management problem. So this is also an opportunity for us to introduce applications of reinforcement learning. So I'll discuss that once I describe the scenario. So what are we looking at in the stochastic inventory problem? The most highlighting feature is that the demand is not certain. We don't know demand with guarantee. So we only probably know the we probably know the probability distribution of demand. That is known. Later on, we will probably relax that also. That's when we will get into Q learning and all that. But we are right now assuming that the probability distribution of demand is known. Right. So this is what differentiates it from the deterministic dynamic inventory problem. So this is a stochastic dynamic inventory problem where not only we are stretching the time axis, but we are also making the demand stochastic. Okay. So the everything else remains the same, which essentially means that in every decision epoch, the decision maker looks at the current inventory level, decides how much to order, which essentially decides the state variable in the next time period, and so on. Right. So the problem is a typical inventory optimization problem where we need to decide how much to order in every time epoch. We need to look at how what is the current inventory level, what could be the potential demand because we don't know demand for sure, and then decide how much inventory to order from our upstream suppliers. Right. So that basically remains exactly the same. Right. So every time the order is placed, the decision maker incurs some kind of ordering cost. We have looked at CO as our ordering cost, right? And that trade-off also remains exactly the same. So if I place too many orders, I'm going to incur ordering cost. However, if I decide to order fewer times but increase the order quantity, then I may incur what is called as the holding cost. And right, that was my carrying cost CC or CH, right? Because the inventory has to be carried in a warehouse, so warehouse has to be rented. So the storage facility, the cost of maintaining the storage facility, all that we have discussed, right? So the essential features of the inventory optimization problem remain exactly the same, just that demand now has a probability distribution, right? So let us get into the detail. Before we get into the detail, let me highlight some of the standard, very often quoted references from where we have used our notations and our model building. So these are the two famous references. I refer to these two books very often. So the first one is the classic Martin Potterman's book on MDPs, Markov decision processes. Right. I happen to have a 2005 version. I honestly don't know whether there was a version that came out after 2005. Abhijit Gosavi's book, even though the focus of the book is on simulation based optimization, there is a very detailed description of MDPs through exhaustive search and why exhaustive search fails, and therefore we need to use some clever method, some method using a Bellman equation, and therefore policy iteration, value iteration, precisely what we are going to do in this session. Therefore, Gosavi's text also becomes very relevant, right? Most of the references actually use the notations that were first used in Potterman's book. So Potterman's book has kind of become a classic now. We will use the same notations. Most of the times our notations are going to be similar to what Potterman had used in his text. Okay, so what are the assumptions of the model? The assumptions of the model, as we said, are first of all, demand is discrete. Demand is 1 2 3 4 5 6 7 8, right? Otherwise the summation sign becomes the integral sign. Let's not worry about that for now. Computationally complex, and therefore let us assume that demand is discrete for now, right? The delivery from the supplier is instantaneous, which means that there is no lead time. We had discussed about this issue when we spoke about deterministic dynamic inventory optimization problem, right? It does shift the state updations by that much. Remember, L was our lead time. If we were to consider lead time, so we place the order in this time period. I get the order only in T plus L time period, and therefore the state update has to happen accordingly. Here the problem is much more complicated than what it was in the dynamic deterministic case, because now I don't know what the demand is going to be in the T plus Lth time period, but I'm going to receive the order that I am placing now only in the T plus Lth time period, right? So all those complications will have to be solved. Therefore, since we are describing the problem first, let us not get into those complications, and let us say that as soon as the order is placed, the shipment is received instantaneously, right? The demand is IID random variable, right? It has a very stationary PMF, and the probability that demand is equal to J is essentially Pj, right? Doesn't depend on T, right? Doesn't depend on T, which that's what makes it stationary. So it is IID, right? When we talk about RL towards the very end of the session, we will probably say that, well, these assumptions can be relaxed, because we are going to actually forecast these probabilities using the data that we have, using the history that we have collected, and so on. So, but right now, let us start by saying that there is a discrete PMF Pj, that the demand is actually equal to J, right? And the warehouse, remember, this was the same assumption that we had used in the deterministic dynamic case. A warehouse has a capacity, which means that the state variable can only be up to M. State variable cannot become more than M, because you can only store so many units in the inventory, right? And we are going to make a further assumption that inventory is non-perishable, which means that I can store the inventory for how many time periods I want. The only thing is, the more I store, the more I will incur the holding cost or the carrying cost, right? Those are the assumptions. We are also going to assume that demand that is not met on that particular day is essentially lost against back ordering. Remember, we had looked at back ordering previously. We are going to right now say that demand is essentially lost, which means that we better ensure that whatever demand can be met should be met, because once the customer goes away from our shop, we are assuming that the customer doesn't come back, or we cannot ask the customer to come back after 2 days, 3 days, 4 days, and that would have been back ordering, right? So we are not considering back ordering right now. Where does it have an impact? Remember, where does it have an impact? It has impact on state updation, right? How does a state variable get updated? So what are the sequence of events? Sequence of events is, this is the beginning of the time period, this is the end of the time period. So very typical, the ending inventory from the previous time period becomes the beginning inventory of the current time period. So this is the start of the time period, this is the start of the day, this is start of the weeks, this is start of the month, and this is end of the time period T. This is end of the time period T, right? So we observe the state variable, which is the inventory level, and that is ST, right? Based on that, I place the order AT. AT is my action variable, that is my decision variable. That's what I'm trying to find the optimal value for, using all this stochastic dynamic programming and all that. AT is my action variable that tells me how many how many quantities to order. As soon as I place the order, remember we said the delivery is instantaneous. So immediately right here I get the inventory delivered to me, whatever I had ordered. Therefore my inventory at hand becomes ST plus AT, which can be used to satisfy the demand. Now demand can happen any time during the time period, right? This is your DT. Unfortunately, I don't know the value of DT a priori. I only know the probability distribution. However, as I realize the demand, I will actually know the value, but I have to place the order even before I realize how much demand I am going to see in that particular time period, right? And then the time period, and then the demand is incurred, the demand is realized. Sometimes I'm able to meet the demand using ST plus AT. Sometimes I'm not able to meet the demand using the inventory that I have plus the order quantity. Whatever it is, I incur some cost, I incur some revenue, right? Whatever I'm able to sell, I generate revenue. plus I may have spent on some ordering cost whenever I place the order for 80, right? All that will happen. I may have to pay for my raw material, buying this quantity 80, I may have to pay something. That cost is incurred, and the time period ends, and then I update my state variable. The state variable for the next time period will be essentially whatever was available at the beginning of the time period, st, plus whatever was delivered in this time period, which was 80, minus dt, right? Minus dt. Dt is the demand, and therefore this is the amount of inventory that I will have to carry to the next time period. uh, Therefore this is the amount that will have to incur the holding cost, right? This order quantity gets into my warehouse, and it is carried for the next day, which means overnight it stays in my warehouse, and therefore this will incur the holding cost, right? As we said, the demand that is not met is lost, which means that we have to ensure that this guy is greater than or equal to 0, right? Most of the time, because we don't know what the demand is going to be, therefore we cannot guarantee that it will always be greater than or equal to 0. But we are saying that if dt is more than st plus at, right? If dt is more than st plus at, since we are considering the lost sales case, then we are simply going to say that demand was more, therefore all the inventory was exhausted, and therefore how much am I carrying from this time period to the next time period? I'm only carrying a 0 inventory from the current time period to the next time period, right? We will not allow the inventory to become negative, because negative inventory would actually mean back ordering, right? Figure out what are the implications of considering the back ordering case. Right now we are not going to consider in this session. All right, so how do we formulate this problem as a markout decision problem? We need stage variable, we need state variable, we need action variable. So let us define all of that. Actually we did little bit of that in the deterministic dynamic case. Let us recall all that, and let us define all these things. So what was our stage variable? Stage variable was the time, right? The days and the months and the weeks, right? So we can think of having a finite time horizon, n days to be considered in the problem. Sometimes the problem is infinite horizon problem. So t will go all the way from 1 2 3 4 5 6 all the way to infinity, right? So there are finite horizon markout decision problems, there are infinite horizon markout decision problems, but essentially time is our stage variable. What is our state variable? State variable is our inventory level, right? Inventory level at a particular time t. st is our state variable, right? If we were to consider lead time, our state variable becomes two-dimensional. Not only do we have to keep track of how much inventory do we have in hand, which would be st, we also have to keep track of how much inventory is on order, right? So there the state variable will become st and yt. Yt is the general notation used for inventory on order. So remember, once we consider lead time, I place the order in this time period, I may receive the goods only L time periods later. Therefore that part, whatever I ordered in this time period, will go into yt, will not immediately get added to st. Here we simply said st minus st plus 80, right? Here we said st plus 80. Can't do that if we consider lead time, because that will only be part of the yt variable, which is inventory on order, right? Let us not worry about that. Right now our state variable is a single dimensional st, right? St is the inventory level at time t. What is the action variable? Action set is how much to order at time t, right? Looking at the starting inventory, I can only look at what can be the potential demand. I may not know the exact demand. I still have to decide how much to order in each time period. And once again, ordering 0 is admissible, right? I may say that, well, I am carrying enough inventory from the previous time period, I don't need anything in this time period. That is perfectly acceptable. So at equal to 0 for a particular t is an admissible value of at. Not doing something is an admissible action, right? That's what we mean. So the reward function is slightly involved, so let us discuss that in detail. Reward function is generally denoted by r, right? R is st and at. At time period t, we had a state variable value of st. We took an action of at, right? We took an action of at. Therefore, what is my immediate reward? My immediate reward is whatever money that I get by selling the inventory, right? Obviously I'm buying it from my supplier so that I can sell it to my customers, right? That's the whole point. This price is supposed to be known and fixed throughout the time horizon. We are not changing that. We may change it, but whatever is the price discovery, we know, right? We are assuming that we get to fix the price, and therefore we know the value of the price. There is no stochasticity associated with price. The only stochasticity is associated with the demand, right? So this expected value is with respect to demand and not with respect to the price. Here, how much will I be able to sell? I will be able to sell minimum of dt or st plus at, right? Remember, I can sell only what I can have, right? I cannot sell more than what I have. So if let us say I carried an inventory of st was 4, right? I decided to order 2 more quantity. So the total inventory at hand is 4 plus 2. So I can only sell 6 units. As long as demand is less than 6, I will be able to I'll be able to satisfy all my customers. However, if the demand is more than 6, I can only sell 6 units, and therefore it is minimum of dt and st plus at, right? So this is the revenue part. Plus my action quantity is 80. This is the amount of inventory that I order in this time period. Therefore, I may have to incur the ordering cost, CO, ordering cost. Remember, inventory problem, classical inventory problem is always a trade-off between carrying cost or holding cost and ordering cost. How much? Sorry, this is a mistake here. This should be a st plus at minus dt. st plus at minus dt, right? We discussed that. How much inventory do I carry? I carry st plus at minus dt amount of inventory in my warehouse, right? And I don't allow this stock to become negative, and therefore we are considering the case for lost sales, right? So that's the reward function. But this is what is called as immediate reward, right? Therefore it is denoted by r. R is always the notation for immediate reward. Then there is future reward, which will be represented in the dynamic programming formulation, precisely what we had done in our deterministic dynamic inventory case, right? But we'll come to that. We'll come to that in the next slide. Okay. So what is the terminal condition? If I assume a finite time horizon, what's going to happen in the last time period? In the last time period, whatever inventory is left over, right? Whatever inventory is left over, what will be the inventory that will be left over? In the last time period, you are going to start with beginning inventory of Sn. You may place some order An. You have to meet the demand in the last time period, which is Dn, right? So this is the amount of inventory that is left over in the nth, which is the last time period. There is no future beyond this, right? Because this is a finite time horizon problem. In a finite time horizon problem, I always have to worry about the terminal condition, and what we are going to assume here is whatever is left over inventory that is salvaged, and we have some function, right? We have some function. Once again, an need not always be 0. So I would say this is also a typo, right? This need not always be 0, because if you start with a starting inventory of 0 in the nth time period and you realize that you have to meet the demand, so why would you not meet the demand? So you will place the order. So n need not always be 0, right? N need not always be 0. N plus 1 will always be 0, because there is no n plus first time period. You are not going to place any order in the n plus first time period. So n plus 1 would be 0. N need not always be 0. But the assumption is in the last time period, actually this is n plus 1 everywhere, right? N plus 1, n plus 1, n plus 1 everywhere, and then it will make sense, right? Then it will make sense. So in the n plus first time period, n plus first time period, the only thing you are going to do is salvage the inventory. You are not going to incur any new demand, right? Therefore, in the n plus first time period, you generate income by selling your leftover inventory, and your leftover inventory is going to be Sn plus 1, right? So if this is Sn plus 1, then all of this makes sense, right? All of this makes sense. So sorry for the typo. We can always correct it. Okay. All right, so let us continue. We have formulated all the things needed for MDP formulation. Now let us get into the equations, right? Let us get into the Bellman equation. How do we formulate the MDP? How do we update the state? First of all, as we have consistently said, the state is going to be updated as st plus 1 is max of st plus at minus dt 0. This 0 is needed because we are not going to allow st plus 1 to become negative, right? So if st plus at minus dt is negative, the state variable is going to get updated only as 0, right? This is obviously under the assumption of lost sales. If we were considering back ordering, the state update would happen like this: st plus 1 is equal to st plus at minus dt, and therefore if dt is bigger than st plus at, then st plus 1 would become negative, and therefore you are actually carrying negative inventory to the next time period. So what would negative inventory mean? Let us say that st plus 1 is negative 3. What would st plus 1 equal to negative 3 mean? It would mean that there are 3 customers who came to my shop, wanted to buy something, let us say pen, or that's what the example that we had taken in the last session. They wanted to buy a pen from me. I recorded their order. I told them, boss, I can't deliver the pen right now, I don't have inventory. I will give you the pen 2 days from now. Please come to my shop and pick up the pen. And I did that for 3 of my customers, right? Therefore, the inventory is negative 3. So what do I have to do? Probably not after 3 days. Come back tomorrow and I'll give you your pen, right? That's what we mean. So tomorrow, what is going to happen is the first thing I have to do, right? First thing I have to do is forget about meeting the demand for tomorrow. The first thing I have to do tomorrow is to make sure that I keep the 3 pens separately for the customers who had come yesterday and asked me for the pens, right? Therefore, from the next day's inventory, I'm going to pull 3 products out. Therefore, the inventory has become negative, and that's what would happen if we consider back ordering. This is called back ordering, right? You tell the customer to come tomorrow, or you deliver the product to the customer tomorrow, and all that will happen, right? The back ordering cost will have to be incurred, right? Back ordering cost, there is typically a back ordering cost because you have lost the customer, right? You not lost the customer, you have asked the customer to come back tomorrow, so there may be a transportation cost and so on. So if we had considered back ordering, we would have updated the state as st plus 1 equal to st plus at minus dt, but right now we are considering with the max function. All right. So what is the objective function? Objective function is maximization of reward over a particular time horizon, right? We will discuss that little later. But this is not a minimization problem. This is maximization problem. Where was our reward? Immediate reward. Immediate reward was here. Immediate reward was whatever revenue I get by selling the inventory minus the ordering cost minus the holding cost, right? That is the immediate reward that I get. Plus I may get some reward in future, so that will be the discounted reward, right? So that maximization of the total reward is my objective in solving this MDP. All right. How do I update my state variables? The state transition probabilities. This is new. This was not there in the stochastic. This was not there in the deterministic dynamic inventory problem because there was no need to update probabilities, right? There was no need to update probabilities. So here we use a Markovian transition probability matrix, right? Markovian transition probability matrix essentially means that what will be my state variable tomorrow only depends on what is the state variable today. It does not depend on the history, right? So where am I today? I am at a state variable S. I have taken an action A, and therefore that is going to dictate the state variable that I may get into tomorrow. I may get into at t plus 1. Currently my state variable is S. My action variable value is A, right? So this is a typical Markovian probability transition update, right? And M, what was M? M was the warehouse capacity, right? Remember, M was the warehouse capacity. So you trust me, right? M was the warehouse capacity. So now that I have come back, let me show you that warehouse capacity was M. warehouse capacity was M, right? So we will not allow the state variable to become more than M, right? Because that's the warehouse capacity. So there cannot be a situation that my S prime is more than M. Can't happen because S prime can only be up to M. Therefore the probability transition matrice, probability transition values will be governed with this M, right? Yeah. uh, Exactly. So why is this zero? Why is this zero? Let us say that you are currently at S. You have placed the order for A, which will be delivered immediately. So what is your time at time t? At time t, what is your total inventory? Your total inventory will be S plus A, right? S plus A. Now there may be some demand, right? There may be some demand which is D. Now even if this D is zero, the maximum inventory that you can carry to the next time period is S plus A. The maximum inventory you can carry is S plus A. You cannot carry more than S plus A because that was the maximum inventory that you had in the current time period. So how can you carry more than that in the next time period? This demand, right? This demand is going to be always non-negative, right? It may be zero sometimes, but it is going to be positive, right? Sometimes. So this demand is never going to be negative, and therefore you cannot carry more than S plus A, which is what is governed by this, right? So S prime, if S prime is in this interval S plus A to M, you can't have this situation. Therefore the probability is going to be zero, right? Now S prime could be between 0 to S plus A, but S plus A has to be less than or equal to M, because that's what would have happened in the previous time period, right? You can carry only M in the warehouse, right? And therefore that is governed by S plus A minus A, P of S plus A minus S prime, right? This is the probability that the demand was actually S plus A minus A prime, right? That is the probability of demand. Now there could be a possibility that you had more than what inventory you were carrying. The demand was actually more than that, right? If the demand was more than S plus A, then your S prime will be 0. Right? But you have to ensure that you are not carrying more than M at any point of time, because that's how much the warehouse can hold, right? What is the probability that demand was more than S plus A? What is the probability that demand was K, where K was bigger than S plus A? That is all Pk, because Pk, remember, demand had a very stationary PMF, Pj was the probability that the demand will be equal to J. Here we are talking about K, where K is any value which is bigger than S plus A, right? Summation of all that is the total probability that the demand was more than S plus A, right? That in those cases, the next time period inventory will be 0, right? You will carry 0 inventory to the next time period. So you cannot carry inventory between S plus A to M. You may carry some inventory between 0 to S plus A. That is when the demand is S plus A minus S prime. And if you have just too much of demand, then you will carry 0 inventory in the next time period, right? So those are the 3 possibilities, and those are the corresponding 3 probabilities. So this is our state transition probabilities. This is what creates what is called as TPM. What is TPM? Transition probability matrix, right? Transition probability matrix. Similarly, there is something called TRM. TRM is transition reward matrix, and we saw the reward function. And it obviously depends, TPM and TRM obviously depends on what action you have taken. So you change the action, TPM changes, right? If you change the value of A, what was A? A was the order quantity that I ordered in this time period, right? In time period T. Obviously, if A changes, then the TPM changes, and you see what is the impact of that. And also TRM changes, because the reward also depends on how much was ordered, because that dictates how much inventory can you carry, where you carrying, how much inventory did you order, and how much you were able to sell. All right. So this is how you update the transition probability matrices. Now let us, as we promised, let us look at the objective function a little more closely. Let us calculate the components of total reward, right? Not the immediate reward, but the total reward, right? Ordering cost, what was our ordering cost component? if you are placing the order, right? If AT is greater than 0, which means you are definitely placing the order, what is going to happen? You are going to incur some fixed cost. This was our fixed cost component. And then you are going to incur some cost because you ordered for 2 units, so you pay for those 2 units, right? So that was C into 8, C of AT. C of AT is the variable cost of ordering. But the moment you decide to place the order, you are going to incur fixed cost K. Very similar structure that we had considered even in the deterministic dynamic example, right? However, if you are not placing the order, not only the C of AT will be 0, even your fixed cost will be 0 because there is no cost of ordering as such, right? So that is our ordering cost. This is our ordering cost. Now the reward, right? The revenue. So as we said earlier, the reward is generated from whatever you are able to sell. This is your total inventory that you are carrying. Your total inventory that you are carrying is ST plus AT, right? And obviously, how much can you sell? You can only sell only minimum of DT or ST plus AT, minimum of DT or ST plus AT multiplied by price. We have already always said that price remains fixed. We are going to consider price to be fixed in the time horizon that we are considering. Now, as we said, what is the probability? What is the probabilities here? So let us say that ST plus AT is denoted by U. Let us say DT is denoted by J. Let the demand be equal to J. What is the probability that demand is actually equal to J? That will be PJ, right? That will be PJ. Now let us say that you carry enough inventory much bigger than what the demand was, right? The total inventory that you are carrying is ST plus AT, which is U, and apparently this U is bigger than J, which is the demand. If you are carrying enough inventory than your demand, you will be able to meet the entire demand J, right? You will be able to meet the entire demand J, and therefore your revenue, let us denote that by small f. Small f, your revenue will be price multiplied by J because demand was J and you were able to meet the entire demand. Now this happens with a probability Pj because demand was J, and that happens with a probability Pj. So if this J is lesser than the total inventory that you are carrying, you will be able to meet the full demand and you will actually earn the maximum potential revenue that you were going to earn, which is price into demand. However, if your inventory is not enough, or essentially means that your demand was lot higher, then you will not be able to meet the full demand. You will be able to meet the demand only that is equal to the total inventory that you are carrying, right? So if the demand exceeds the available stock, then the revenue will be FU, right? FU, where U is ST plus AT. Simple, right? So as we said, let us say ST was 2, AT was 3, right? So your total inventory that you are carrying was 5. Now if demand, if J was 7, right? Demand was 7, but you were only carrying 5 units of inventory. And therefore, how much revenue will you earn? You will earn f of U, where price into U is 5. Even though the demand was 7, you will earn revenue only for the units that you were able to sell, and the number of units that you were able to sell was 5, right? And that happens with the probability Pj, where all these J's are bigger than U, where the J's are bigger than U. So U plus 1, U plus 2, U plus 3, U plus 4, all the way to infinity. Summation of all that is essentially the total probability that your demand will be more than the available stock, right? And therefore, what is the value of this FT, which is revenue? It is if the demand is up to U minus 1, right? It will be FJ, right? The revenue will be FJ, and that happens with the probability Pj. And what are all the possible J's? J could be 0 to U minus 1. However, if demand is more than the available stock, then that probability is QU, and the revenue is FU, right? So this is the expected revenue, right? This is the ordering cost plus the holding cost. What is the holding cost? Holding cost is CC, which is carrying cost of ST plus 1, right? ST plus 1, because you are going to carry ST plus 1, which is the closing inventory of the current time period, which becomes the beginning inventory of the next time period, right? So that is fairly straightforward. Now, what are policies, right? Policies are essentially the order quantities, right? Some decision rule, mark out decision rule that assigns an order quantity to be ordered in each time period, right? AT for all the possible STs. Now, AT, the value of AT will depend on ST. If ST changes, AT will change, right? So the available the order quantity that you will decide will obviously depend on what was the starting inventory in that particular time period. So AT is always going to be a function of ST. ST changes, AT changes. Remember, we have actually seen something like that in the dynamic deterministic case. So what is the policy? Policy is this vector AT. Okay, is this vector AT, A1, A2, A3, A4, A5, right? Or sometimes it is called decision rule, right? It is a sequence of decision rules. Sometimes, for example, Puterman's text actually refers to that as DN, which is decision rule, right? In the n stage. Which is how much are you going to place? Actually, once again, this notation is wrong. Okay, so this was an of 1, an of 2, an of 3, right? Because this is your state variable. All the way to S. Your state variable can be anywhere from 0 to S, where S is the maximum value. Here that S is M, because you can carry only so much of inventory in your warehouse, right? So this notation, again, I'm sorry for this, because this is not AT, right? This is not T1, T2, T3, T equal to 1, T equal to 3. That's not what we want. It is a vector, right? In time period 1, what you are going to do. In time period 2, what are you going to do? Time period 3, what are we going to do, right? And so on. So not only that, what are we going to do in time period 1? If the state variable is this much, if the state variable is this much, if the state variable is this much, and all that, right? So it is a sequence of such decision rules. A very famous example of this policy, one such policy, is order sufficient stock to ensure that inventory reaches capital S. Right, place these orders whenever inventory at the beginning of the time period is less than S, right? So whenever ST is less than S, you place the order in such a way that your ST plus AT is actually equal to this capital S, right? So that's what this policy means. Place the order whenever your beginning inventory is less than S, and order so much that your total on hand inventory reaches capital S. Whenever the beginning inventory is more than S, which means if ST is greater than S, then don't place any order. Then AT will be actually equal to 0, right? So this is example of one such policy, right? So this is obviously a stationary policy, very stationary policy, doesn't depend on time. It only says keep looking at your beginning inventory. Whenever beginning inventory is less than small s, place the order. Whenever the beginning inventory is more than S, don't place the order. How much do you place the order? You place the order in such a way that your total on-hand inventory is actually equal to capital S, right? So that's a famous SS policy, right? If you want to read more about SS policy, enough books on inventory management that speak about this policy. This was only an example of such policy. But once again, what are policies? Policies are essentially sequence of decision rules that tell us exactly what do I need to do in every time period. Not only that, it must tell me what do I need to do in every state I may find myself in, right? Not only every stage. What do I do on day 1? What do I do on day 2? What do I do on day 3? Right? Not only that. On day 3, if I find myself in state equal to something, what do I need to do? Right? State 3, state 4, state 5, state 0. Right? What do I need to do? Right? So policy should tell me that. Essentially, that's our decision variable, right? That's our entire decision variable. Remember, the vector of A's, and A obviously depends on S. So let us take a numerical example for this. Let us put some numbers to this abstract idea so far. So let us put some numbers so that we can actually solve it. Okay, so what is ordering cost? Let the capital value, capital K, be $4. Every time you place the order, you incur the cost of $4 irrespective of how much you order. And how much you order, the variable cost depends on $2 per unit. So if you place the order for 4 units, you are going to incur 4 into 2, which is $8, plus this $4, therefore $12. Remember, we have tried to keep the costs similar to what we had encountered in the deterministic dynamic case. Okay, holding cost. Let us say every unit of inventory kept in the warehouse incurs $1, right? So u units of inventory will incur u dollars. So every unit of inventory incurs $1, right? That's what I meant. Salvage cost, let us assume that there is no salvage cost, essentially meaning that whatever is left over inventory, that is a waste. We may assume some value here that may change the ordering policy because there is some value to it. Right now, let us assume that there is no salvage value. Revenue, let us say that I should have put a dollar sign here. So what is revenue? It is price into units, right? FU, where U is the unit sold. So it is $8 per unit of sales. Okay, so that's our cost function. Inventory cap is 4. We can carry only 4 units of inventory in our warehouse. Let us say that we are looking at a very small problem, only 3 time periods. We have tried to keep things similar to what we have done in the deterministic case. Here, because of Bellman equation and because of the objective function that we are going to use, we may need one more parameter, and that is called discounting factor. Discounting factor, I'll explain that in the next slide. Let lambda be the discounting factor and let the value of lambda be 0.95. Doesn't make sense to have a discounting factor which is more than 1. So essentially, what does that mean? It means that a dollar tomorrow is only worth 0.95 today, right? So bird in hand is, right? You know the phrase. So if you give me money tomorrow, that's not worth as much to me as you would give me money today, right? So $1 today is not worth. Actually, I said it the opposite. $1 today would only mean 0.95 tomorrow. All right. Density, very important stochastic problem. Therefore, I have to tell you the probability density function. So probability is equal to 1 with a demand is equal to 1 with a probability 1/4. Demand is equal to 2 with a probability 1/2. Demand is equal to 3 with a probability 1/4. And there is no other possibility of demand taking any other value. And therefore, probability is 0 at all the other places, right? So demand can only be 1, 2 or 3. And the corresponding probabilities are 1/4 plus 1/2 plus 1/4, which is equal to 1. And therefore, axioms of probability are met. So these are the only 3 possibilities of demand. Demand can be 1, demand can be 2, demand can be 3. Remember, we have tried to keep the problem a very simple problem. Okay, so how do we start? We start with the Bellman equation, of course, but the probabilistic Bellman equation. In the previous session, we have seen a deterministic version of the Bellman equation. So let us do that here. So how do you do that? At time period t, what is the optimal value of being in state S and taking an action A? There is some immediate reward plus the expected future reward. Expected future reward is this, right? This is ut plus 1 of being in state J, but I could be in any state J, right? That probability is governed by me going to state J given the fact that I was in state S and took an action A, right? So this was my element of TPM. This is my element of TPM. Currently in time period T, I am in state S taking an action A. Demand is realized. Because of demand realizing, I may land up in a different state at the beginning of the next time period, right? At the beginning of the next time period. So this is the probability, this is the utility that I get, or the reward that I get from t plus 1 onwards. So this is the expected reward of all the future, but I have to discount it to the current value or discount it to the current time. So I have to find the present value of it. So lambda is my discounting factor. So this is the Bellman equation for the probabilistic version, right? Earlier we didn't have this P of J given as S and A, right? So this is obviously conditional probability. I do realize that I have skipped a lot of portion where I could have explained to you what is a TPM and all that. Right now, take it that these are Markovian transition probability values, and therefore they get into some kind of matrix, and therefore that matrix is TPM. So the Bellman equation is going to be of this format. right? Now you can take the limits of all that, and or if the problem is finite time horizon problem, remember we solved the deterministic problem also using backward induction. We can also do that in this case, right? So we will actually start with the beginning inventory of the fourth time period, which will be the closing inventory of the third time period, because our time horizon is only 3, and there is no salvage. We are not going to get anything by selling anything in time period 4, right? What are we going to sell? We are only going to sell the leftovers. We are not going to incur fresh in demand. We are not going to incur fresh ordering, nothing, only selling of whatever is left over. But apparently that also doesn't get you anything, right? Because that was the assumption. So most of the finite time horizon problems are solved using backward induction. We can solve it using backward induction. How would we solve our numerical example? Let us do that. So let us solve the problem at time period 3. At time period 3, it's a very trivial problem, right? Because there is no U4, right? There is no U4. There is no future, right? So the expected future cost is going to be equal to 0. There is no salvage, right? So everything is 0. So what happens in time period 3, which is the last time period? You incur only the immediate reward, right? So what is the objective in the third time period? The objective that you have in the third time period is you start with some inventory. That inventory is S. You take the order, you place the order, which is A, in such a way that you meet the demand, right? You meet the demand, but that's about it, right? You want to be just enough, because if you have leftover inventory, that is going to have no value at all, but you will incur the cost of ordering that excess inventory, right? So you just want to order. So whatever maximizes this immediate reward is the objective function for time period 3. Time period 3 starts by you sitting in a state called S and you taking an action called A, right? So based on the numerical values, you can actually calculate what is the best policy, what is the best action that maximizes the reward, immediate reward, only immediate reward. There is no future reward when we are in time period 3. However, when we are in time period 2 and time period 1, we have to worry not only about the immediate reward, but we have to also worry about what state transitions I'm going to make, and what I'm going to earn from next time period onwards, right? So the Bellman equation will be fully utilized. Currently the second part was 0. That will get utilized completely, and that will be slightly more involved calculation. So we will solve the t equal to 2 problem, and then we will solve the t equal to 1 problem, and then we would say the entire problem has been solved, right? Because we are using backward induction. Right now I leave this discussion here, and obviously after this we will have a Python demonstration of the same numerical example, where we will actually solve this problem and tell you what is the optimal policy, which essentially tells us what to do in each time period if we find ourselves in a particular state variable, right? So that is a numerical example, and that is the example of a finite time horizon problem, and that is solved using backward induction of the famous Bellman equation. Now this is a simple example, right? Inventory problem is solved. Now what can be complications? What could be complications? Right now, since we wanted to keep this problem very small, we said, well, hold on, warehouse can only accommodate 4 units of inventory, right? So your S, your state variable, can only be 0, 1, 2, 3, 4. That's all, only 5 values. And therefore your TPM, the transition probability matrix, is a very small matrix, right? 5 by 5 matrix. What if this possible values of state variable is huge, which means TPM is large? Remember, if TPM is large, computation of this future reward becomes complex, right? Calculating that becomes complex. So what if this TPM is very large and very unwieldy, right? Unwieldy. What if I am solving an infinite time horizon problem? Right? How long will you keep doing this? Right? If it's an infinite time horizon, you can't obviously go backwards, because there is no last time period, right? So you'll have to essentially look at some other algorithm. In those cases, backward inductions will fail us, right? Backward induction will fail us, and we need something better than the brute force implementation of Bellman equation, right? We need something better. What are the 2 or 3 most famous methods to solve these kinds of problems then? The first method is essentially value iteration. So first of all, we have to understand what is a value. Okay, so what is the value? We use optimality equation, right? Optimality equation. What is the optimality equation? Let us say that Vn is the value of being in a state S at a stage n. What is the value? Value is the maximization of not only the immediate reward but all the future rewards from n plus 1 time period onwards, being in state J, where J could be anywhere in my state set of possible values of the state, right? Obviously discounting factor, right? And the possibility that I may hit state J if I'm in state S today and taking an action A is obviously governed by TPM. Maximization over all the possible values of A will essentially give me the value of being in state S at a particular time n, or at a particular stage n. If I were to take the limits of this, an infinite horizon equation actually becomes something like this, where value of being in state I, right, value of being in state I today is essentially maximization of immediate reward, immediate reward because of that action A, plus all the future rewards. And remember, since it's an infinite time horizon problem, the future that looks the future that is visible from today onwards will be very similar to the future that looks from tomorrow onwards, because it's infinity, right? So we drop the subscript n plus 1, we drop the subscript n, and so on, and we only say that the value today is being in state I, which is state Vi, and the value tomorrow will be Vj, because we are in state J, and J is essentially added. So I'm taking an expectation over all the possible states that I may end up being tomorrow onwards, right? What is this Vj? Vj is the expected reward, not expected reward. After we multiply with Pj, it will become expected reward. What is Vj? Vj is the value of sitting in state J tomorrow and earning a future reward from tomorrow onwards. That will include immediate reward that you are going to incur tomorrow, plus all the future from tomorrow onwards, right? So essentially Vj is that future. Multiply that with Pj, you will get all the future rewards, discount that to the present time using lambda, and add that to the current reward, immediate reward that you are going to get by being in state I today and taking an action A, and you maximize that over all the possible actions, right? So how do you run a value iteration? You run a value iteration assuming that you don't know the value of these V's, right? You don't know the value of these V's. Obviously, you are going to assume that TPM is known. You know the state transitions. You obviously know the immediate reward. You know how to calculate the immediate reward, because we have seen, right, the revenue that you earn, the expected revenue that you earn minus the cost of ordering minus the cost of holding, that will go as part of R. The probability transitions are known, lambda is known. So we are going to start a value iteration by assuming that this Vi and Vj are variables that I don't know. I have to find the values of. I may start with some arbitrary values, right? So how do I start arbitrary values? I'll start by setting some V0, and I will select some threshold. I'll tell you what is the purpose of this threshold. Let us start with n equal to 0 and keep incrementing. So for all values of S, we calculate this guy. Where we plug in this V0, right? So when we calculate V1 of S, we will use V0 of S, and V0 of S is arbitrarily selected. We may select all the V0s to be 0, doesn't matter, right? We'll select some values. Of V0 for all states. So we will have to assume V0 of 1, V0 of 0, V0 of 1, V0 of 2, V0 of 3, V0 of 4. That's it. Five values that I have to assume, because my state variable cannot be more than 4, and therefore these are the 5 values that I will have to assume. I have to select some values, right? And based on that, I will calculate the value of Vn plus 1, right, which is maximized over all possible actions that I can take, which maximizes my immediate reward plus the future. Here V0 will be known when I solve it for V1. Keep doing this, right? And essentially check if the gap between Vn and Vn plus 1 is very small, right? Some threshold, some lambda prime. Actually, if you refer to Putterman's book, if you refer to any standard text on MDPs and particularly value iteration, there is some equation which depends on some guy called lambda, some guy called epsilon, and obviously lambda, which is the discounting factor. I'm going to right now assume that all of that has been taken care of in this lambda prime, right? So threshold, once again a typo, this has to be 3. So if this Vn plus 1 and Vn are very close and they are less than this epsilon prime is the threshold that I have set, then we are done. Actually, we can stop the value iteration and we can go to step 4. Otherwise, we have to increment n by n plus 1 and go to step number 2, which is to calculate that again. We will calculate Vn plus 2, use Vn plus 1 here and keep doing that. What happens if we go to the stopping criteria? This should be 4 because that was step number 4. So essentially, we have a policy. We have an optimal. It is called actually epsilon prime policy. Optimal policy. Optimal policy is going to be given by whatever action maximizes the total value, the immediate reward plus the future values, right? So argmax. So what is the decision if you are in state S? The argmax of all of this will give us the optimal policy in this particular state, right? Obviously, we are assuming. So this is not the optimal policy. This is called epsilon prime optimal policy because I am assuming that the gap between Vn plus 1 and Vn is small enough, right? So this is how you run value iteration. Fairly straightforward implementation of the Bellman equation. Hope this is okay with you. Let us go quickly to policy iteration. Right, policy iteration. You assumed values of in the value iteration. We assumed values of V0. Here we assume values of V0. In policy iteration, we start by assuming a particular policy. Right, select a policy at random. Right, select some policy. N equal to 0. Select an arbitrary decision rule. Some arbitrary decision rule D0, which is a set of all the admissible decision rules. Right. So select that. Now there are 2 steps in policy iteration. One is called policy evaluation. One is called policy improvement. First, for this arbitrarily selected decision rule, evaluate the policy. Right, policy evaluation. Here you solve for unknown Vn's by plugging in the value of D0. Right, here you know the D0. So here you know the values of A and therefore you calculate the Vn. Here everything is known. You know A, you know the state you are in, right, and therefore you will be able to calculate the immediate reward. You know the TPM, right, you know the TPM, you know lambda, so Vn is the unknown guy. So essentially you solve for this and you get the values of Vn, right, for all the possible states. This is for a particular decision rule which gives us the value of A. But decision rule essentially gives you the order quantity, right, in every state. So you solve this Vn and remember how many decision variables are there. When you say we have to solve for Vn, there are essentially 5 decision variables, Vn of 0, Vn of 1, Vn of 2, Vn of 3, Vn of 4, right? So 5 decision variables you solve for the given policy. Then you improve the policy, right? Improve the policy. Now at the n plus first step, you choose a dn plus n such that you maximize this maximize this value. Maximize this value, right? Maximize this value, which is immediate reward plus all the future expected reward discounted, right? This is a discounted reward policy. This is a discounted reward objective, right? So what is your dn plus 1? Dn plus 1, which is a new decision rule in the n plus first step. N plus first step is you are trying to improve because you are trying to find the action that maximizes not only the immediate reward plus all the future expected discounted rewards, right, from that time onwards, from tomorrow onwards. Generally when we select dn plus 1, we try to select dn plus 1 as elements of dn itself as much as possible. Sometimes they are different. When does the iteration complete? The policy iteration algorithm closes when dn plus 1 is actually equal to dn, then we stop, right? Else we increment n by 1 and then go to policy evaluation again, use dn plus 1 here and solve this Vn and then select the next decision rule and keep doing this, right? Here what is the optimal policy then? The optimal policy, when we stop, the optimal policy is dn plus 1 which is essentially obtained by taking an argmax of all the possible actions, right? Okay, so this is the policy iteration. Okay, one last thing to be discussed, which will take us very close to, which will take us inside RL, which is called Q learning. So when do we use generally Q learning? So far we have been debating about this Bellman equation, where this is the TPM, right? What if we don't know TPM? When we do know TPM, that MDP is essentially called model based MDP, when the probability transition matrices are known, right? However, if the transition matrices are not known, then that is called model free MDP. Model free MDPs are when the probabilities are not known. In those cases, what do? We start by defining a vector of q's, right? A qt, which is in the state space of S cross A, number of states multiplied by number of actions for each time epoch, right? So we define a sequence of vectors. And how do we update these vectors? We update these vectors by this equation, where qt plus 1 of S and A, you are in state S and taking an action A, right, is given by this expression. You keep updating this, and this is essentially becomes what is called as Q learning. So this is essentially Q learning. So what we will do is we'll stop here. We will demo all of this. By the way, what is this alpha t? Alpha t in Q learning is essentially the rate of learning, the rate at which we are learning. Right. So this is our attempt. This is essentially our attempt to calculate the expected rewards even without knowing the probability. So essentially, we are learning the probability transitions. So alpha t generally refers to the rate of learning, right? So more of these details when we actually discuss Python example of all this, right? So essentially 3 methods: value iteration, policy iteration, and Q learning. There are many methods, right? Once we say Q learning, then we can argue why not TD, right? Temporal difference method. Many methods, but the drill is going to be similar, right? The elements are going to be very similar. Just that computational complexities will force us to take that particular method. All right. So let me end the session here, and we will follow this up with a Python example of everything.